designs of pierced vaults through form finding and digital fabrication by Riberi and Manuello.
Thank you.
Okay. Let's share the screen. Okay. Good morning, and thank you for the great opportunity. In these few minutes, I'm going to show you the main part of the study I have done with Professor Amedeo Manuello. Our goal was to show the great potential of masonry structures, particularly how masonry vaults can be also today an innovative architectural and engineering solution. The goal of increasing the openings for natural light and the importance to save material led the research to study pierced vaults typologies. We studied the form-finding process to design the geometry of pierced vaults starting from few governing parameters, such as the slenderness ratio and the holes pattern on the vault surface. Different funicular structures have been analyzed in order to compare them to identify the best shape together with its hole pattern configuration. Different form-finding processes have been evaluated. The multi-body rope approach proposed by Amedeo Manuello and the truss network analysis developed by Philip Bloch have been applied with the support of RhinoVault, a free tool for Rhino. The design of the structure started with a squared geometry with a side of 16 meters. Different slenderness ratios have been considered, together with different holes pattern configurations. The TNA, starting from an initial planar hypothetical vault projection, found the equilibrium solution using static graphic principle, while the MRA based the principle of the form finding on the falling of masses connected by ropes in the time domain. Each geometry solution has been analyzed with a FE solver, LUSAS modeler and solver. A backlink analysis has been completed to study the global stability of each structure, and the first critical load multipliers have been recorded. To evaluate all the results of the analysis, a graphic representation have been realized. The first critical load multiplier values and the critical live load, that means that self-weight is not included, have been represented in function of the pierced area percentage. It has been noticed that for each hole pattern configuration, when the hole in the center of the vault is considered, the critical load multiplier is always higher than the holes pattern configuration with lower pierced area percentage. Also, the solution is always more stable if the holes are concentrated in the central part of the vaults. Moreover, the first critical load multiplier is always bigger than 1. That means that each structure designed with the TNA and MRA is able to carry at least its self-weight and additional vertical distributed loads, both symmetrical and anti-symmetrical. To validate the results of the analysis, one of the most pierced vaults designed has been chosen to be realized as a scaled prototype. With parametrical support of Grasshopper, the continuous surface of the vault has been divided into pieces. These pieces are the basis for the design of the brick for the vault fabrication. Their three-dimensional geometry has been found with Grasshopper. The bricks have been realized in mortar cement with a water-cement ratio of about 0.4. The formworks for each brick that have different shapes have been realized with 3D printing technique in PLA, a plastic material completely eco-friendly. Grasshopper was also used to design the falsework that had to support the bricks during the vault realization. That temporary structure has been realized with cardboard sheets placed on a plywood square panel, supported by 4 threaded bars that allow to control the height of the temporary structure. All the bricks have been placed on the upper surface of the falsework. At the end of construction, the spar has been removed. In this phase, the self-weight of the structure started to be carried. Hold the spar has been removed. In started to be carried out on the structure. Image correlation has been used to underloading. An incremental vertical load has been applied on the structure, and the deformations have been recorded. The DIC performed qualitative information of the structural behavior of the structure, and the deformation observed during the FE analysis were recognized in good agreement with the DIC displacements on strain measurements. So the DIC analysis can be used to extract measured parameters to recognize in advance the collapse condition of this kind of structures. Thanks for the attention.
Thank you, Federico. We have time for just one very quick question. So did you perform some loading test on this structure? I've seen in the preview material that you did it, but I didn't understand if it is loaded just vertically or also asymmetrically, maybe.
Yeah, we in the analysis, in the FE analysis, we did both symmetrical and anti-symmetrical analysis to secure of the structures. It has been designed also only for vertical loads, and the geometry of each structure we analyzed is designed on vertical loads. One of our future step is to introduce horizontal loads such as seismic loads or wind load, because we want to understand the behavior of this structure if loaded with horizontal loads. So it's a future step of our study.
Okay, thank you very much.